Okay, so yesterday we started in on a bunch of like trig identities where it was like theorems that kind of help us relate numbers that aren't like the basic four that we typically know. So we did the one that was Pythagorean where we used like a squared plus b squared equals c squared. Then we had an opposites one where the signs kind of switch around. And then we had half turn one, and then supplements was the last one we were working on. So this example two here is going to kind of lend to that supplements one. So it says here that we're given sine of 172 is approximately 0.1392. Find a value of x other than that number 172 between 0 and 360, of which the sine of x is equal to the same exact thing. Okay, so what I would want to think here is if I've got my unit circle, sine of 172 would just be like a little bit above the 180, right? So if that's like our sine of 172, like out to there, they want to know what other sine value is going to kick out this same answer, okay? What I would think here is I'd think, okay, is my sine value, is that the x or the y?
The y.
That's the y, right? So basically I want another value there that's going to kick out the same exact height. So basically we just got to figure out how many degrees it would go out right there. Any thoughts on that? They'd be like a reflection over there. 8, right? Because wouldn't those be like supplements of each other? Yeah, so here if this was like 8 in that direction, here this is 8 in this direction, so those should be at the same exact height. So sine of 8 degrees would also kick out 0.1392 because their height is exactly the same. I guess approximately that, not exactly that. So I guess you probably just need the 8 on that. But that all has to do with those adding to 180. So we got the 8 by doing 180 minus 172 to get that 8 degrees. Okay, so then we got one more theorem to do here. And this one, the picture is not actually in the book. They didn't have a picture for it. So I just drew one. The theorem is on there. So jot that theorem down, and then like I said, the picture's not in the book. I just made one up to kind of match the other pictures. So you have to jot that picture down from there as well. Okay, so let's take a look at this last theorem here. So complements theorem, kinda ish like the supplements theorem, like setup wise, but then like the answers it kicks out are different. But for our complements theorem, complements add to 90, right? So basically, if you've got your theta there, whatever degrees that is, your one that's going to be 90 minus that theta is just going to be like back from the 90-degree line, however far that same amount there. So what that ends up doing is it ends up being reflections, this time not over this line like it was for supplements, but it's actually a reflection over the y equals x line. So then what that ends up doing with our coordinates, if you had like cosine of 90 minus theta, when it kicks out an answer, it's actually whatever your sine of theta originally was. Okay, so basically the cosine and the sine just switch around places with each other because they're reflections over that y equals x line. Okay. All right, so let's look at our last one on the example sheet then. So this one, there's a lot of different things we got to kind of solve out here, so we'll just kind of work them step by step. So we're starting off with that our sine of x is equal to 0.681, and our goal is to find all of these things. So the first one there is our cosine of x. Okay, so we're using just one of those theorems or stuff we already know about, like unit circles and stuff, to kind of walk us through and figure this out. So if they give us a sine of x and our goal is to find the cosine of x, I would use that Pythagorean one. So for A, I'm just going to write the name of which one I'm going to use off to the side. So I'm going to use the Pythagorean one. And it doesn't say you have to do that, just for a reminder later if you're working on this. So with that Pythagorean one, it's always our cosine squared of theta plus our sine squared of theta is always equal to 1. So here, if we know what our sine is, we can take that and put that in for like the sine here, but we would just have to take it to the power of 2 since it's sine squared. So we could just take that number, 0.681 to the power of 2's equal to 1, and then drop down our cosine squared. I'm going to actually switch it to x instead of theta there because it's got an x in our directions, but same difference. And then I just solve that out, so I'd go on my calculator and I just take that 0.681 to the power of 2, get 0.463761 is equal to our 1, cosine squared x. And then obviously to get rid of adding, we subtract. So you're just going to subtract that number from each side. And you could probably round in there. You don't have to write the whole thing out. I just did. So then when that's gone, then we're left with cosine squared x is equal to 1 minus that number, which I get 0.536239. And then similar to just a normal equation, even though it's like cosine there, if it's squared, to get rid of it, we square root. So you're going to square root on both sides. So then we'd be left with cosine x is equal to, and then you just do the square root of that number on your calculator. Oops. Square root of 0.536239, and I get 0.732. I'm just going to leave it at that. And it would be approximately that because I'm rounding. And then also there, if we did the square root of it, we would have to have that plus or minus with it, right? So we did that square root. Okay, and then tangent-wise then, if we knew what the, so for part B, to find tangent of x, if we know what the sine and the cosine of x are, couldn't we use that to find the tangent? Yeah, what's the formula for tangent? Sine over cosine, right? So for like our tangent of theta, it would be sine of theta divided by cosine of theta, right? And this isn't one of our theorems, but it's just definition of tangent, if you want to know tangent, where that came from. So then we would just take our approximate there for the sine one. I guess it's not an approximate, but we would put that one in. So tangent of x would equal our sine of x, which was that 0.681, divided by what we had for that cosine of x, 0.732. And then you just divide that out on your calculator. 0.681 divided by 0.732. Now I get approximately 0.930, somewhere in there. Okay, so now we get into another one of our theorems. So now they want sine of negative x. So what I would do is I would look through my theorems that we just wrote down and look to see which one's starting with sine of like a negative theta. So which of those, like Pythagorean, opposites, half-turns, supplements, or complements, has one that's like sine of negative theta? Anybody? The opposites one is what I would use, yeah. So this one we're going to use the opposites theorem. Because it says in the opposites theorem, if we've got sine of negative theta, it's going to kick out negative sine of theta. So what that means is if we put the opposite value in there, which is what they're asking, because our question's asking for sine of negative x, that's going to kick out the same value we had before for sine of theta, but the negative version of it. So all you would have to do is you just put a negative there, look back up to the directions of what it kicked out for the sine, so the 0.681. And it's just negative 0.681. So some of them are simple like that, where they just kick stuff out. You just kind of have to follow what the patterns are that they give you. Next one here is also one of them that we wrote down there. So now they're asking for sine of pi minus x. So in our notes, it would be like sine of pi minus theta is what you're looking for. So looking through your stuff, what does that match up with? It's the supplements one, right? Because supplements add to 180, but isn't pi on our unit circle the same as 180? It's halfway around. Yeah, so it's the supplements one, and with that one, if it's sine of pi minus theta, that's just going to kick a sine of theta out. So that just means like whatever you started with, you just keep the same thing. So if ours is like sine of pi minus x, that's just going to kick out a sine of x. And what was our thing for sine of x? The 0.681, yeah. So it's just the same exact number as what we started with. So like I said, some of them aren't too bad. We don't have to calculate too much. And that was the supplements one. See where that one comes from. And then the last one for E, now they want cosine of pi plus x. So pi plus theta is what we're looking for. That's the half turn one. So the half turn's the one that we always do 180 plus our theta amount. Again, the pi stands for 180. So we're looking for, it's going to kick out negative cosine theta. But really, to be able to come up with that, don't we need our actual original cosine before we can kick out the negative cosine of it? Yeah, so what I would do here, didn't we find cosine of it before? Yeah, so our cosine of x from before was that approximately 0.732. So when we do this out, if we're doing cosine of pi plus x, it's just going to be whatever answer we had for that cosine with that negative in front of it. So just, I guess it's approximately again, negative 0.732. And those are kind of a lot. It's kind of a lot to figure out what they're asking and then put that into what they're trying to get you to interpret and all that stuff. Okay? Okay. All right, so that's it for notes. So you got a good chunk of time to work here. So page 240, 1 to 26, skip 11, and skip 22.
Can you go back to the 2?
Sure can.